All righty. Good morning, everyone. Can you hear me?
Yes, we can.
Yes, we can.
All right, that's tremendous. So let's have a little difficulty logging in here, but I got it all figured out now. All right, so let's see. Let's bring up our business for today, and the last new business of the semester. Isn't that wonderful? Come here, files. Need to bring up 9.2 because that's where we'd finished last week. And then 9.3. And I'll scroll down to where we need to be in just a second there. Let's get 9.3. I want to go ahead and get that T distribution chart up and ready. Maybe I'll bring up the normal also. That won't hurt. And let's get that one going. And I'll wait a little bit before I log into the homework. Well, are those gonna? Oh, all right, looks like. Okay. Looks like that's, okay, now I'll get the share screen going for us. Let's see what we have here. Now, let me scroll down because we did hypothesis testing last week using the p-value method, and we stopped right before the second method for doing this. Now, in the real world, you'd most likely use technology and the p-values, but I still like to show this method also, especially when I talk about the next section with the t-values. We'll see more why we're going to use this. Now, these critical values that we're going to call them, I know we also use the term critical values for confidence intervals. That's true, but this is a different critical value. Now, using p-values, that shaded area was the p-value. Now it's no longer the p-value. On a left tail test, the shaded area is the alpha, whatever the level of significance is. And then this z-value, which will be negative, corresponds to what would be the value with that area to the left. Now we come over to this one. It's just the mirror image of the other one. The right tail test, it's that same alpha. And the Z alpha here will be a positive number, and it represents that area to the right. So for example, if that was 0.05, this Z alpha would technically be the same thing as the 95th percentile, because it would represent 95% to the left. Two-tailed test, there's always two critical values. There's always a plus and a minus. And the reason why I set this alpha over 2 is because it divides that alpha in half, because that way the two pieces add together to be alpha. So you got alpha over 2 to the left, alpha over 2 to the right. And they're the same number, due to symmetry, it's the same number on each side, but there'll always be a plus and minus associated with a two-tailed test. So what how we reject, and we'll talk about the statements, how these fall here or whatever. But the idea on this is, you know, the p-value, all we did was look to see if the p-value was less than alpha to reject. If it wasn't less than or equal, we'd fail to reject. Now this one, based on whatever this area is, if the test statistic falls in the shaded region, you reject. If it falls in the blank part, it's fail to reject. So you just kind of have to sort of see where it goes. For example, let me bring up a scratch page here and not very good. All right, I'll say I'm doing a left tail test over here. And let's say that's negative 1.96. That's one of the common values. Okay. And let's say the test statistic was Z equals negative 2.5. Okay. So it's on a number line that negative 2.5 would be somewhere, doesn't matter exactly, we don't have to hit the right spot here. Let's just say somewhere it'll be to the left of negative 1.96. And therefore it falls in that shaded region. So in this case, we would fail to reject. We would reject. So reject.
Professor Smalley?
Yes.
Sorry, we can't see this screen, I don't think.
Oh, did I do something wrong on the share screen here? I wonder what I did.
We can see it, but if you're drawing or doing something, we can't see.
Oh,
anything.
you saw when the notes were up, but you're just not seeing this.
Right.
Oh, all right. Well, let's look and see what happened here. I don't know what. All right. I thought I did the universal share screen here. Well, I'll stop it and start it over again. All right, screen. Let me hit share. What do you see now?
Looks like I can see the notes now, yeah.
But not my scribble.
No, yeah, I can see the scribble there.
Okay. Okay, I must have done. Sorry about that. Yeah, I'll go. Oh, yeah, the notes aren't up there. I guess I should. That's why you're not going to see the notes. You have to go back to them. But you're saying you didn't see this part before here, right here. Okay.
Yeah, right.
All right, that's fair enough. So anyway, negative 1.96, and if it was negative 2.5, it would fall to the left of that region on the number line. So we would reject if it falls in the shaded part. So let's say if the test statistic would have been like Z equals negative 1.2. On a number line, that number is going to fall somewhere here to the right of it. And this one we would fail to reject. So we'll put this in a formal statement here in a minute. I go back to the notes. So hopefully you'll see everything I put up here now. So back to the notes. Yes?
Yes.
All right, there we go. So now, okay, that's good. I don't want you to see every time I move the screen. I want you to be able to see what's there. All right, now we're going to use that t-distribution chart to do this, to get these critical values. I mean, we could do the inverse. You could do it with technology. If I was going to ask ones that weren't on this chart, then yeah. But if I'm only going to ask ones that are on this chart, we don't have to really worry about it. But yeah, you can kind of do it with an inverse norm technique. A little trickier with a two-tailed. But anyway, now the rest of this section will just be using the Z distribution, so just the top row. Now the next section will go back to the degrees of freedom business. So we'll go back to that, and that's where we'll do the n-1. Now the confidence level stuff was pretty straightforward. And you take everything off top row. Now this one's a little trickier because you have to choose between one of two rows. And notice there's some similar numbers there, like 0.1 and 0.1, 0.05, 0.05, 0.01, 0.01. So you got to choose the right row. The way to do that is left and right-tailed are both one-tails, meaning one shaded region. The only difference is when it's a left tail, see, notice the values on the chart are only positive. When it's a left tail, you just have to know to take your number and whatever you get from the, or whatever, for right now, it's just this row. And you just got to put a negative sign in front of it. You just make it negative. If it's right-tailed, it's also one-tailed, so it'll be the same number. So for example, left-tailed 0.1 will be the one-tailed 0.1. It'd be that number right there. It would be negative 1.282. The right-tailed would be the same thing, except it would be positive 1.282. Now, two-tailed means you have to look at the, okay, that one's pretty straightforward wording-wise, I think, you know, two-tailed, there's a row just for two-tailed. Two-tailed, so two-tailed 0.1 would be a column over to the right. It's 1.645, but two tails automatically have a plus and a minus. There's automatically two numbers. So it's plus and minus 1.645. And we're going to, you know, practice this a little bit here. It's, you know, you don't have to be an expert in the first 5 minutes here. So let's see it in action a little bit and see what we, you know. Anything's kind of weird or strange when you learn it at first. Now, this is just sort of the wording here on what we call the decision rule for this process, how we make the statements. The decision rule for p-value, you know, for p-value is just p-value less than alpha you reject. Here's how you say it. This is just the formality of how you say it. For a left tail test, we're going to reject the hoe if z is less than that negative z alpha, the negative one tail value. If it's a right tail test, we reject if the z is greater than the positive. I didn't write positive, I just wrote one tail there. You wouldn't have to change the sign on the chart value. And a two-tailed is an or. You reject the hoe if z is less than the negative z alpha over 2, or if z is greater than z alpha over 2. And you go back up and look at the two-tailed, it's or because the number's not going to fall in both rejection regions, but nor is it expected to. If it falls in one of the two shaded parts, it's reject. If it's anywhere in the middle, it's fail to reject. All right, so let's just, here's one where it's just said left-tailed alpha 0.01. You know, what kind of statement do we make here? For how would we make our decision rule? Well, right off the bat, the first thing, you know, we could do is we could write reject hoe if z is less than, you could even put the negative sign right there if you wanted to, because there's no doubt that's going to be negative because it's left-tailed. So all we have to do is go to the chart and find the 0.01 one-tailed value and put a negative in front of it. That's where you got to be careful. So here's 0.01 one-tailed. And look right here below it. Oh, not all those numbers. 2.327, but it's negative. So you'd reject, and I just drew a little shading picture of it. So it means your test statistic falls somewhere out in that red shaded part. That's rejection land. Oh, we just did this one. Right-tailed 0.10. We just did, I didn't realize that was coming up, or I would have used a different number. But yeah, right-tailed 0.10. Right-tailed is going to be positive. Let me highlight it again just to show you. There it is. And here it is right here. But it's positive because it's right-tailed. So there's that one. Two-tailed Two-tailed is automatically going to be in the format of reject hoe if z is less than some negative value or z is greater than that same value as a positive. So it's always going to take that shape, that format. You just have to get the number. So be very careful. There's 0.05 in both rows, but now we want the two-tailed 0.05. This isn't that difficult, but if you're just not quite paying attention, you know, you could misread and look at the wrong row. And there's the 1.96. Ta-da! And we'll see that when we go look at the homework here in a little bit too. But I'm intentionally doing this by this method. And one thing about these is and I mentioned that a little bit last week, even though we didn't know how to do this method yet, I did mention that, you know, your decision to reject or fail to reject is the same no matter which method. In other words, if you said, well, I did the p-value method and I got reject, and then I used critical values, I got fail to reject. There's only one answer to that question. You did something wrong. One of those is wrong because they have to yield the same conclusion. So that would be pretty bad news if they did not yield the same result on rejection or not. So that's the answer I'll tell people. That means you clearly got one of the two wrong. Okay, so we're going to do this one. I think I might have done the p-value on this one. Yeah, I just didn't do the whole process I showed you in the calculator. But we'll see that this matches up. But we're just going to humor it and do it this way, you know, even though it could be done the other way. CEO claims firm's office staff is more than 8.5 hours. All right, more than, that's pretty straightforward. More than, remember more than is greater than from what we learned last week. Greater than is always a ha, and it pairs up with the less than or equal to, you know, so none of that's changing. You know, we still have the same three pairs we've always had. Let's see, I just wrote down all the data right here. Now, this is a right tail test by definition. So our decision rule using this method will be reject the hoe if C is greater than, okay, here's 0.01. So I want the right-tailed 0.01 value, which we've already gotten that one from above, but let's do it again. Right-tailed 0.01. Right-tailed is one-tailed, just like left-tailed is one-tailed. 0.01, yeah, we already did this one. That's okay. 2.327. And so we're going to reject the hoe if the test statistic is greater, Z is greater than 2.327. So one thing that these two methods both share in common is they use the test statistic, but in different ways. You know, you still use that, but we do it a little differently. P-value, you just use the test statistic to get the area, which is the p-value. Here, you look and see if the test statistic falls in the region or not. All right, I'm not going to go through the calculation of the test statistic. There's the formula. And you can always get this if you're using the TI calculator, you can get that in there if you want to. If you don't feel like using this formula and you just want to do the Z-test, that's okay. Nothing wrong with that. 3.55. I'm pretty confident the 3.55 is somewhere in that shaded region greater than 2.327. I think we can safely say that with no doubt. So since 3.55 is greater than 2.33, we reject the null hypothesis and we support the claim that the mean workday is more than 8.5 hours. Now keep in mind the wording here. The only time that you can support a claim technically is if the claim is the alternative and the hoe gets rejected. In other words, let's say if the claim was the null hypothesis and you failed to reject, that is not evidence of supporting that claim. Remember, you never fall in love with a null hypothesis. You just may not be able to say it's wrong. But if we reject the hoe in favor of the alternative hypothesis, we love the alternative hypothesis. It's not absolute proof. We just personally love it. And we feel strong about it. So this kind of supporting the claim needs to be based on rejecting the hoe and the alternative was the claim. All right, there's the z-test with the p-value. And obviously this better also be reject, like I said. And look at the p-value, scientific notation. You just move it over 4 zeros, less than 0.01. And that's also leads to reject. So there we go. Now, we didn't have to do all that. I just wanted to show you. We will on the homework here in a minute. Remember last week I was just picking on the p-value parts of those problems in 9.2. Now I'll go in there and I'll do the entire problem. P-value, just so you can see that again, and then the this new method. All right. Should be almost done with this, yeah. Let's see. Coffee shop claims mean caffeine content of 140 per cup. All right. Of pretty much means equal. It's like is. It just would not be grammatically appropriate with the word is there unless the rest of the sentence was written differently. Have a mean caffeine content is 140 per cup. That wouldn't sound right. Okay, here's all the data. You sample. There's a sample mean, standard deviation, population standard deviation. That's what allows us to be a Z. Level significance 0.05. We're going to do it using rejection regions. And like I said, you can you can always, do it p-value as a check whether or not you reject, but obviously if I might have a question on the test where I often do that, okay, just give me the decision rule in terms of these statements. So you would still know how to have to write that based on looking it up on that chart. But yeah, you could still get the conclusion using p-values if you wanted to. That's fine. Okay, what do we got? It was 0.05, two-tailed. We've also seen that one, but they do tend to repeat themselves. Two tails, 0.05, 1.96, always a plus and minus. And as always, for two tails, always written this way. We're going to reject that hoe if Z is less than negative 1.96 or if Z is greater than 1.96. There's the test statistic, 1.77. And this one's like the graph kind of helps a little bit, I think. Well, not unless you're doing p-value, but look at 1.77. I'm thinking it falls between these two numbers somewhere. Obviously, it's on the positive side, but it's not greater than 1.96, is it? So somewhere right about there, wherever, no matter if I have it in the exact right spot. The important thing is I don't have it in the shading, which is correct. So I'm going to say fail to reject. So once again, and on this one, failing to reject doesn't mean you support the claim. It doesn't mean you agree it's 140. You just don't have the evidence to think you think it's wrong. All right, so now I did the p-value using a chart. Since most of you are using the technology, there's probably no point in me explaining this part right down here. But this is just how you get the p-value if you're using the chart. But up here, look at the z-test. It's 0.77, which is what I got right there, 0.77. 0.0768. Well, anyway, 0.77, 0.768, rounded. That's greater than 0.05. So p-value greater than alpha, fail to reject that O. All right, let's take this one out. Scroll back up. Somehow everything got shifted down a little bit in my notes there. That just bugs me. I know they were all on the right line at some point. Fast food outlet claims the mean waiting time in line is less than 3.5 minutes. Ugh. I don't know if that means that factors in people, how many in front of you, or if you just walk up and only one person's in front of you. I don't know. There's probably a lot of questions to be asked here on this, but probably means when you get up to the counter, I guess, to get your deal. Get your stuff. Well, whatever. So less than, okay, straightforward, less than 3.5 minutes. So less than is automatically an alternative. It pairs up with greater than or equal. And let's see, so here's 60, and it'll be 60. Mean was 3.4 minutes. Population standard deviation 0.6, and then our alpha is 0.05. So we're going to test it by using this method. So let's look at our decision rule. So automatically left-tailed is going to start out the same way every time. Reject ho if z is less than negative, whatever that's going to be. 0.05, one tail, 0.05. So it's automatically going to have the negative because it's left tail. And I know it's kind of blurry. It's hard to see this, but you'll have this chart stuff with you. You can see that it shows it as a negative. Even though it says T, it's going to be the same for Z and T, meaning when we get to the next section for T's, left tail test will be negative, right tail will be positive, and two tail will be plus and minus. Same thing. Well, there's the 1.645. There's the test statistic done just with the formula. There it is using the z-test. So I got this, the calculator got this. Everybody got negative 1.29. Now, what I'm showing you right here, this picture on the left, that's really the correct process. But I've had students, and yeah, so I can see why this could be a little confusing. It's a little trickier sometimes with negative numbers to know which one falls on what side or the other. So one thing you can do here is convert using symmetry. If you flip everything over to the other side, it's really the same image. It's the same thing. So what I have on the left is really technically the right way to do it. But flipping it over, you might be able to visualize this better and go, oh yeah, 1.29 is definitely not greater than positive 1.645. So it's fail to reject. So that's only if you have issues with this. Of course, then the p-value backs it up right there. 0.098 is greater than 0.05, so that's fail to reject. So we fail to reject. We do not support the claim because the claim was the alternative and we didn't reject. So you would have to reject to support it. So we don't support their claim it's less than 3.5 minutes. All right, we'll do this one. I'll write this one out. May not look pretty, but I always like to save this one. We'll do it the same method. But like I said, I'll put it in the calculator so you can also see that. That's how I'll get the test statistic, and then we'll also look at the p-value. All right. I'm going to save my voice, so I'm not going to read this problem. Still coughing, and so I'll let you read the details, and I'll just get the ho and the ha. And it says less than, right? So less than. 34,000. And that means the hoe would have to be square and equal to. Now, let me get the statement here. I'm not going to write all the stuff like sample mean, standard deviation. You're going to see me put it in the calculator anyway. I mean, if you're not sure, you can feel free to ask. But like those other problems, I kind of wrote the information down. I don't think we need to do that. Less than is going to be negative something. 0.05. One tail. $1.645. Oh no, it's the notes. Oh, let's do the t-test. Oh, I gotta wake up the calculator. Well, while that's waking up, let me draw a little graph here. Just to give you a visual. Come on, calculator, wake up. Just thinking about it. Come on, calculator, you can do it. Yay. I'm going to keep flipping back and forth. It was 34,000, I think, or 34.5. 30, 34, 34. Dang it. Dang it. This was 33.5 down here. Tickle. Took a cough drop. Let me try another one. Dang it. I feel fine other than that cough. Not sick or anything. Well, I've had some allergy symptoms and stuff. Don't have the runny nose or sneezing anymore, but stupid cough won't go away. 54. $1,200.
Professor, it's 33,550.
Oh, okay. Thank you.
Huh?
No, I forgot. All right. 54. And to got to pick the right one here, which is the middle one. Golly. There it is. Negative 2.7, whatever. Let's see. That's going to go out here somewhere. So we reject the null hypothesis and we support the claim that the mean lifetime is less than 34,000 miles. We like that claim. Let me go back to p-value just to show you that. We'll reinforce our conclusion. 0.0029. So 0.0029 is less than 0.05. So that just verifies the reject. Ta-da! Okay, now it's my math lab time. Oh, wow, that's there. I don't need this. We'll do a couple of those, and we'll go on break. Not as bad last semester when I tried to, we were doing this stuff when I had COVID, and I tried to do a lecture. The cough was even worse, and I just felt terrible. Now I don't feel terrible. I feel fine. Yeah, it was, I think people felt, I'm sure they felt sorry for me. But I think the last couple sections I had to post, I already had just recorded lecture videos from those, not like the way we do it before I started doing it this way. And I just posted those so they would have something, because I'm going, look, I don't think I can get through another lecture while I have this thing. Agony. Yeah, now I was agony. This is just more annoying. Annoying to me, and I'm sure annoying to you. Okay. It's probably good I'm doing this in private, because coughing around out in public, people might start yelling at me. I think I'm passing it to them. I've been checking my fever, no fever. Hadn't had fever since then. So I'm 99.999% sure that it's not COVID. I've had shot 1 out of the 2. Yeah, any one of these would be good. Yeah, these are one. Let me check that they have everything with it. That should be good. Yeah, critical score. We couldn't do that last week. Yeah, this is a good one. I'll uncheck it. We'll do the whole thing for this one. I like this one. All righty. Suppose university advertises its average class size is 36 or less. That sounds like something that UHD would probably advertise. Might be a little higher, though. I definitely get 40 in this class a lot, so maybe they say 40 or less. Now, we got to think about what symbol goes with this. 36 or less. That's not the same as less than 36. 36 or less, I think that means less than or equal to. What do you think? We'll find out, won't we? And then the other one automatically has to be the one that pairs up with it. Greater than. Ta-da! So we okay? 36 or less is not the same as less than 36. Z-test statistic. Well, I'm going to go right to the calculator here. I figure that's the way we've been doing things. And I'm guessing by this point it's probably the same set of attendees here, you know. So, the few, the proud, the Marines. Oh, golly. I hope I was on the right thing, wasn't it? All right, so 30 SC. So we know 36, what we're testing against. I'll try to memorize a little bit at a time here. 36, 43, 38.7. Well, let me just do 36 and 43. I don't get these two numbers. 38.7 and standard deviation is 9. And this was a right tail test. Remember, that's always based on the alternative right there. Right tail because, you know, less than or equal to paired up with greater than. So it's always based on all right, let's see. I always forget to check how many decimals at once. 2. I guess 0, 0, 0, 7. Just 0, 7. Huh? All right, I typed something in wrong. It's gonna be my. Oh, N is wrong. Oh yeah, I messed this up. Standard deviation is 9. Oh, that's what it was. Okay, that's 9. This is 43. Let me double check the 43, but is it 40? Yeah. All righty. Well, I guess rule number 1 is to put the numbers in there correctly, wouldn't you say? I think that's probably a good idea, right? I'm going to go 0, 2 this time. What's wrong now? Am I still typing something in wrong?
I think you put in the p-value.
Oh, good Lord, yes, you got it. I put in the p-value instead of the, yeah. Thank you. It's 1.97. I entered the number right below it. Good, there you go. You got it, that's it.
Let you slide. You're coughing a lot, so you know.
I wish I could say that was affecting my vision, but that would be a lie. Oh, good grief. Well, okay. All right. I hope I hadn't intimidated you, but I'm sure, well, yeah, I'm sure you wouldn't have screwed this up, but like I did, but yeah, like last semester, I did this 2 days a week. So sometimes I could just, if I knew I had screw ups like this, I could pick which one I thought was the better performance, and post that for both classes because it didn't matter, technically. So I don't have that luxury this semester. So, all righty. Okay. Grief. But it's kind of funny because even though I typed in the p-value the first time, I did have the numbers in wrong anyway. So, but I didn't think I did that time, and I did not. Critical scores, 0.01 is your alpha. Right-tailed, so it's going to be positive. Right there. 2.327. Okay. So yeah, we'll probably do two-tailed one here, but yeah, it was two-tailed. I think you can just put like negative of the number, like it says, and then use a comma. They're not, you don't have to put like a plus and minus symbol in front of it at the same time. You would just do negative, comma, positive. Actually, I think it can go in either order, but I like to do the negative first. 2 point, how many you want? 2. So 2.327 will be 2.33. But yeah, that's what they mean by separating answers if it was a two-tailed test. All right, we're getting it done now. Now, if you, I'll be happy to do a little picture, but it's up to you if you can do it without, whatever. Let me come up. I'll just use this one, that's fine. Okay. So it was 2.33. I'll change that to red. And the other test statistic was like 1.97. I would have to say on a number line that 1.97 is going to be somewhere to the left of that number. What do you think? So if it doesn't fall in the shading, that means not reject. But we'll get to back this up with a p-value also. Of course, you could use the p-value now if you wanted to instead of that, because there it is. And 0.02 is greater than 0.01. That's what this alpha was 0.01. So that's reinforces the fail to reject. In this case, no, actually you got to get this wording right either way though, less than the critical value. Now you got to be careful of the wording when it's on the negative side. I'll show you what I mean here in a second. Do not. So that wording does not automatically go together every time. It would for this one. Let me go back to that picture. And I'll just use the same, so I have to redraw another one. Let's say it would have been a left tail test. And this would have been negative 1.97. It still would have been fail to reject. But notice on a number line, the easiest way, negative or positive, if it's on the right, it's greater. But this one, it would have been because the test statistic is greater than the critical value. That would have been the actual correct wording, but it still would have been do not reject. So that wording part is different whether it's on the positive side or negative side, but it still would have been do not reject. So that's maybe where the picture could help a little bit. Or I guess you can, as long as you know whether it's reject or not, I guess you can just narrow it down by trial and error, I guess, but do it and then you can change your answer, I guess. In other words, if you already knew it was do not reject, I guess you could change that choice, whatever. P-value, 3 decimal places for that. 0.25. Fantastic. Okay, let's do one more of these and we'll go on break. think I'd like to intentionally look for a two-tailed here. Got it. There it is. So if it's okay with you, might as well just do this one. I don't think there's anything too weird in the remaining problems. Let me look and see. Less than. That's another less than or equal to. We already did that. Okay, this would accomplish the same thing as the one I'm about to do. Credit card balance of 1,076. Let's see. Okay. Okay, there's nothing too weird. I'll go back and do that one I was going to do. Just want to make sure it wasn't anything too strange. This will work just fine. All right, copying of 1.8 cups per day. Equal 1.8 we got it. So was equal, not equal. Test statistic. Okay, let's don't mess this up again here. I say us, me. I think it's 1.8. 1.8. I'll go ahead and go down to the means. I know that's 1.9. Now let's get the standard deviation in the end. Standard N is 50. Standard deviation is 0.5. And this is an equal, not equal test. So we have to select that, two-tailed. I mean, to get the p-value right, you have to make sure you get that right. It would give you the right test statistic no matter what, but to get the p-value, it has to know what kind of test it is. Because the test statistic is just using that formula, in other words, so it would use the same formula no matter what you put there. But it's going to affect your p-value, that's for sure, which one of those you choose. All right, well, test statistic, 1.414. So let's see how many it wants here. 2. I'm going to go with 1.41. Got it. Critical z-scores. Two-tailed test, it's going to have a plus and minus. Two-tailed, 0.05. There's 2. Okay, we always got to be careful what row we're on. Two-tailed, 0.05, not one-tailed. 1.96. Well, not all those numbers. Oh. There we go. So it's going to be plus and minus 1.96. I think you can do either order, but I always put the negative first. 1.96, comma, positive 1.96. All right, look at us go. Because the test statistic, okay. Well, I mean, let me do the picture thing again. We might do it without the picture, but I like the picture. Mainly if it helps you or not. It definitely helps me explain it better. All right, we got negative 1.96. And it was 1.7 something, I think. Oh, 1.41. I was completely wrong there. But I knew what region it was going to fall in. I remember 1.41. So let's give it a light blue color there. I don't know. Now we'll use this image to see how they're phrasing the question. It's definitely do not reject. That's for sure. Because you see it didn't fall in either end. Anywhere in the middle is do not reject. That much we know for sure. But let me see if they use any kind of crazy wording here. Yeah, I can automatically do this. That's right. Looks, I wish they would use the word between. Falls within the critical values. In my mind, that makes me think it's between the two numbers, and I hope that's what they mean. Or does that mean it's in one of the, if it's not this one, it's the bottom. It does not fall within the critical values. Maybe it is this one. It's just the wording is poor here. In other words, do they mean by within, or do they mean in the shading is what I'm getting at. So if they mean within the shading, then the answer is D. If they don't, then it's this one. I'll try this one, then it's got to be the other one. Okay. Then it meant what I interpreted it as. But you can see it's kind of weird though, doesn't it? Within kind of means it makes it belong. I don't know. I'm probably overthinking this. You probably figured it out in 2 seconds, and I made it too hard here. P-value? Oh, how many decimals? 3.157. And that's clearly failed to reject because 157 will be greater than the alpha. Look at us. We got this mastered now, don't we? All righty, break time. Our usual 10 minutes, okay? All right, and I'll go ahead and just bring up the other notes. I'll go ahead and pause the meeting. That way I don't have to edit it out later. Pause recording. All right, I'll see you in about. All righty, so let's see. Let's get back over here to 9.3. Welcome back to my loyal and faithful crowd there. And this ought to flow along pretty well because this section, and we'll go to the homework, is because number one, it's just we're summarizing. We know what the t-distribution is, which I'm going to go back through that in a second. And we now know the basis of hypothesis testing. So now we're just going to apply that to problems that are T's. And it's going to be, the only issue is they will still have to make the one-tailed, two-tailed decision. But instead of using that top row on the chart, we're going to have to go to the correct degrees of freedom row, just like you do for confidence intervals. All right, so here's the reminder what makes it a T. I noticed I wrote within n-1 degrees of freedom. The original population must be normally distributed. That's not true for the other one. The central limit theorem pretty much implies that X bar will be normally distributed. We don't have the population standard deviation. We have the sample standard deviation, S. Usually these are small samples, but that's not always the case. Don't assume that. But in our world, you know, for test purposes, that actually will be true. Anything I keep under 30 is going to be a T. And just like I mentioned before with confidence intervals, the idea is that if n got really, really large, T and Z are basically the same thing. But there's quite a significant difference with smaller samples. And that's usually what T is used for anyway as smaller samples, although it doesn't have to be. It can be used for larger. But at some point, you'll reach a value where it wouldn't make much difference, in other words. Okay. Now, one-tailed, okay, same idea as before. One-tailed represents both left and right, and we include a negative sign with the left-tailed value, exactly like we did before. So is this, two-tailed, plus and minus sign with each value. Now, the wording for the rejection decisions is exactly the same. It's just using the letter T instead of the letter Z. That is the only difference. Well, the right side is always going to be a number, you know, after you find the number, but on the left, it'll be whether or not it's T or Z. That's the only difference. This all pretty much is the same. Now I got this little miniature version of the chart, but I'll go to the big chart here so you can see this. Okay, and we're going to see, okay, we're going to find the critical values. Value or values, obviously if it's two-tailed, it'll be two numbers. And what's this first one? Alpha equals 0.10, n equals 11. So if n equals 11, that means we have n minus 1 degrees of freedom, 10. So let's go to the big chart here. Or I could zoom in on that other one. 0.10, one-tailed, because left-tailed, 10 degrees of freedom, right there. But because it's left-tailed, we must put a negative in front of that number. Negative 1.3722. Okay. What's the matter with me? So you reject the hoe if T is less than negative 1.3722. Right-tailed, 0.01, n equals 22. So it's 21 degrees of freedom. So right-tailed means it'll be positive. So we go to 0.01, 21 degrees of freedom. So here's 0.01 one-tailed. 21, or I already forgot. 21 or 22 degrees of freedom? 21 degrees of freedom. So it's the fifth column. I got to scroll down. It's 21 degrees of freedom. 2.5176. So we're going to reject the hoe if T is greater than 2.5176. Two-tailed, 0.05, n equals 7. N equals 7 means degrees of freedom will be 6. Of course, two-tailed just means two-tailed. Two-tailed, 0.05. 6 degrees of freedom. There we go. 2.4469 plus and minus. So we would reject the hoe if T is less than negative 2.4469 or T is greater than positive 2.4469. Okay. Let's see how we're going to form a t-test. All right, look at the test statistic. Of course, you're going to be using a calculator, but anyway, just pretend like if we needed this formula for sure. But it's basically the same formula as the other one. The only difference is it's labeling the standard deviation as S because that's one of the rules here, but instead of sigma, but it's the same thing. But which the t-test and the calculator is going to get you that. We're going to see that here in a minute. All right, computer repair believes the mean repair cost is more than $95. All right. More than's pretty straightforward. Not, I don't want to try to trick you on the wording there. More than's more than. That's the claim. And then it would automatically pair up with less than or equal to. So 7 randomly selected computer. So it kind of hit a number in there on us as a word. But we'll be all right. So there's your 7 over here for N. 4250 is your standard deviation. And X bar is a mean, sample means 100. So let's do the decision rule. It's a right tail test. We're going to reject the hoe if T is greater than some positive number. So it's N equals 7, so it'll be 6 degrees of freedom, one-tailed, 0.01. Oh, time to slide over one column to the right, because there's your two-tailed 0.01 right there. 6 degrees of freedom, 3.4127. So we're going to reject if the T is greater than 3.1427. And here's the test statistic using the formula. Like I say, I'll show you the t-test here in a minute. And it comes out 0.3113. Well, I think it's easy to say that 0.3113 is certainly not greater than 3.143. So it's failed to reject. And since the claim was the alternative, we fail to reject the hoe. We do not support the claim that the mean repair cost is more than $95. All right, let's put this in the calculator. That's always fun. Stat, test, t-test. And I don't remember. 95 is the hypothesized mean. 100. Wait, 100 is, and then 95 is, I'll double check that. This one's 4250. Last one is 7. So let me check that. Oh no, that was, okay, it was 95. Okay, I have those backwards. But easily fixed. I go to 95 right here. Go to 100 right here. It's a right tail test. Okay. There's the 0.3113 test statistic. Now here's something important I want to mention. In this section, we're not going to directly use the p-values. What I mean by that is you can indirectly use them. You know, if you get the calculator and you look at it, it's there. You can use it to help you determine reject or not reject, but you will not be asked for the p-values on the T. And the reason for that is only people using technology would be able to get it. See, p-values, when we first learned p-values on the Z, you can get them off of the normal curve by looking up the area from the Z value. People aren't at a disadvantage if they don't have this calculator, but you would be here. So I had to go through and gut the homework out on this section and replace any problems that were asking the p-values to ones that did not. So that way people that couldn't get them, you know. But so like I said, you know, you can use that p-value since it's right there in front of you. And the p-value is definitely greater than alpha for this one. That's a large p-value. So it's clearly failed to reject. So you can come up with that part of it, but you will not be asked the p-values on a T, and that's the reason. Maybe someday down the road before I retire, you know, I'll be in a class where, you know, every student's using one of these for sure, and I know they are. Then I could bring that back in. But now, since it can only be found by technology, I'm not going to penalize those without it. Which probably isn't anyone viewing this live, but it could be someone viewing this later. Okay, so anyway, so there's everything. So, all right. Because you might be wondering if you look through here, you know, you're not doing any p-values or whatever. And like I said, I've already taken care of that in the homework too. There won't be any there unless I messed up. Somebody can let me know because you've seen me remove problems before. So let's just, I think, so the rest of this section is just looking at different examples here. I may not do every one of these just so I can get to my math lab homework. But I sort of want to do that very last one that didn't have the workout part on it. A couple others I know I want to do. So if I may skip through these a little bit. Like I said, get to the homework. But I figure every one I skip here, I can do one extra there. Let's see. Nightly lodging family 4 is at least 185. 185 at least means greater than or equal to. So it's the hoe because it has the equal. It pairs up with less than. This will be a left-tailed test. Here's all your information. N is 6, so it'll be 5 degrees of freedom. So alpha's 0.05. So we look up 0.05 one-tailed with 6 degrees of freedom. No, wait. 5 degrees of freedom. 0.05 one-tailed. Right here. 5 degrees of freedom. 2.0150. So our decision rule wording, yeah, just likely you'll have a question because sometimes on these tests, I don't, you know, it's important to know how to do the entire problem, but I may only ask for certain segments of a problem. You know, like it's very likely I'll have a question on the test that, okay, what would be the decision rule for this? And you would just pick the right answer choice out of, you know, 4 or 5 of these things. You know, obviously one of them probably would be if you did not subtract 1 for your degrees of freedom, you know, stuff like that. Sure, another answer choice would probably have the arrow going the other direction, that sort of thing. All right, yeah, so every problem on the test will not be where you're doing this entire thing. But like I said, if you understand the entire thing, you can do any subset of it. All right, test statistics. So 172 is the mean. 185 is the hypothesized mean. 15 over square root of 6 is negative 2.123. Now, that's a little tricky. Now, this absolute value stuff that I wrote here, okay, don't worry so much about that. But if you recall back to the last section where I showed that one problem and showed how you could flip it over to the positive side. That's what I mean by the absolute value there, is if you just mirror image it over, if you weren't sure where that fits, if you mirror image it over, you would see that positive 2.123 is definitely greater than positive 2.015. So you would reject. So let's pop this one in the calculator. I didn't do it before. I'll let you look at it. Looks like I didn't save it because I knew we didn't need the p-value, but just take a look at it. So t-test. And $172, 15, and 6. 172, 15, and 6. And this is a left tail test. Okay. So there's your test statistic. So you can get it that way. P-value, 0.04. Alpha is 0.05. So the p-value of 0.04 is less than 0.05. So that would also lead to the rejection conclusion. So like I'm mentioning, I will not be asking the p-value specifically for t-test, but there's nothing from stopping you to use the knowledge of how it works for you to reach a decision of reject or not reject. Because this business with these little negative numbers right here can be a little tricky. But the p-value then also backs that up. Let me look and see what I might do this one, or I may skip this one. Oh, that's an equals. The next one. Tell you what, I'll skip that one. Not that there's anything wrong with it. Sort of, if you want to look at it and play around with it. But I see the next two I want to do. Local brewery distributes beer in bottles labeled 12 ounces. A government agency thinks that the brewery is cheating its customers with bottles less than 12 ounces. Man, if you cheat people out of their beer, they're not going to be happy, are they? That might cause some riots. That ought to be a federal crime, right? If you cheat somebody out of the amount of beer. Maybe not. So, agency selects 20 of these bottles, measures their contents, and obtains a sample mean of 11.7 with a standard deviation of 0.7, and then use a level of significance of 0.05. And then there's that statement, see sample standard deviation. It's because sample mean, and that implies sample standard deviation. Probably better if I had the word sample there, but if it was meant to be a population, it would absolutely say that, or it could use a little symbol there or whatever, but otherwise you can assume it's sample. You can also assume it's sample probably because it's less than 30, but anyway. Less than 12. Less than's the alternative. So it pairs up with greater than or equal to. So N is 20. Makes 19 degrees of freedom. 0.05. One-tailed. $19 degrees of freedom. How about right there? Of course, that's going to be negative because it's left-tailed. So we're going to reject the hoe if T is less than negative 1.7291. And I calculated, and I got negative 1.92. So I kind of drew the little picture right here. And this is the absolute value thing. It's just the, like I said in the last one, it's just a fancy way of flipping it over to the positive side. All righty. So we reject, and we do have evidence to support the claim that the mean amount in the bottle is less than 12 ounces. Let's see, do the t-test on that one real quick. Okay, no, that's 12. This was 11.7. And it's 20, and I'm going to go back and get the standard deviation. I don't think I even looked at it there before. .7. All right. Left tail test. All right, it's already sitting there at left tailed, so that's good. It's already left tailed. Calculate. So like I said, you feel you can get your test statistic that way if you want to. Nothing wrong with that. But like I said, there's the p-value, and that would also lead to reject because the alpha was 0.05. So 0.035 would be less than 0.05. So we would reject. All right. Okay, let's do this one. I don't know, maybe I'll do that one. Definitely want to do the one that doesn't have the numbers in it right here. The numbers written. I may skip the fluorescent. We're about to do it equal, not equal right now. So I might skip the bulb problem. Alrighty, Big Daddy claims the average GPA for all UHD students is 2.8. Okay, is means equal. So we got equal, not equal. And that's the claim, this times the hoe of the equal. Now, this time we've got the individual numbers. I'm pretty sure that's not going to be on the exam, but it might be in one of the homework problems, and I'll do it if it is. But that's good to understand. We did this with confidence intervals, if you recall correctly. There was a confidence interval problem where all we had was the data. We didn't have the, so it wants us to calculate the stats from the data, which we'll talk about that here in a minute. All right, let me get the critical value first here. Two-tailed, so it's going to be a negative and a positive. 0.05 two-tailed. 8, I know it's 8 because I can count how many numbers. It says 8 also, but you can easily count there are 8 values there. 7 degrees of freedom. .05, two tails, 7 degrees of freedom. So it's plus and minus 2.3646. I don't know why I rounded to 3 there, whatever. Either way, it's okay. Obviously, on a test, you'd be able to recognize the right one. And then the homework will just follow whatever they want. So your decision rule on this, using the critical value method, rejection regions, is reject the hoe if t is less than negative 2.365 or if t is greater than positive 2.365. Now the rest of this, I'm going to skip this because this is if you were, and I skipped it before too, if you were having to use the formulas to calculate the mean and standard to do all the stuff, and I did that before, you won't need to do that. Well, I mean, assuming no one watching it live will, because we're going to be able to put this directly in the calculator, just like we did with that confidence interval problem. None of this would be necessary, but I did it because I probably did this problem a while back when we were kind of doing it a little more old school, I guess. So let's see. Now this is where I've got to build these numbers in a list. Stat, edit, list. So I'll just type over those. All right, is there any way I can memorize 4 of these at a time? I don't know. Could just take a picture of them, couldn't I? I'll see if I can do it. That way I won't do it. I don't have to look twice here. Okay, 27332426 2733 24, 26, 27, 24, 26. Okay, I hope I'll check. That's why I wasn't saying anything, because I was reciting those numbers in my head over and over and over to try to memorize it. Yay! Okay, I don't want to get too cocky here, though. I got to do this batch now. 3, 1, 3, 2, 2, 9, and 3. I think I got it. One through 2. Yay! Treat myself to a cookie or something. Let's see. Okay, I'll quit out of that. And now we go back to t-test. And you will do this as data instead of stats. Data means you're getting it from a list. Stats means what we normally do is where we just enter the numbers. All right, go back and look at this. 2.8, 8, and then, okay, everything else is in L1. That's why it's best to put it in L1. And this was a two-tailed test. So I got to hit that. So only the number it needed was the value you're testing against. It's going to do everything else internally. And it's even telling you the mean and standard deviation, which we go back and look. 2.9 and 3.116. Yeah, there's the 2.9. Okay, 3.117, 3.116. That's just rounding. So yeah, so I got it right doing it that way, but I don't think you need to go through that. So there's the test statistic. Now, once again, I'd be taking a peek at that p-value, and that's a pretty large p-value. Means it'll be greater than alpha for sure. So it's going to be do not reject. Well, let's see, this other way here. 0.91, let's see if that also fits. Okay, I've got 0.89. That's just due to rounding, so obviously I rounded, whereas the calculator uses more decimal places, but that 907 is the same as this 89. Well, it's not the same number, but it's just a little more accurate. But you can see that 0.89 is between those two numbers, so it's failed to reject. Oh, there it goes. Failed to reject. So notice that doesn't mean, if we're not rejecting, it doesn't mean I supported it. It just says there's not evidence to reject that. There's not sufficient evidence to reject the claim that the mean is 2.8. So you see that's kind of tricky. Doesn't mean we agree it's 2.8. We just do not have the evidence to say it's wrong. Isn't this fun? Man, we're winding down to the very end here. I'll skip that one. This is just using the absolute value thing if you want to, but you don't have to worry about this right here. It's not critical. I was just trying to use that as the guide if the negatives were giving you trouble. Let's do this one. This one I'm going to use the calculator. I'm going to write the ho and the ha, of course. Or I think this book, I keep forgetting this other book we used to use, HA, but I've told you that HA or H1 are interchangeable. So if you see H1 in the homework, which I think it is a lot because this book uses really H1, but both of those are fine. Mean greater than 160. So greater than is the alternative. And that'll pair up with less than or equal to as the O. And let me write the decision rule. I can pretty much go this far right here. T greater than, I know it's going to be a positive number. So what is my N? 25. So it's 24 degrees of freedom, 0.05, one tail. So it's 24 degrees of freedom. So third column, 0.05. 24 degrees of freedom. How about 1709? Which I'll just call that 1.711. I mean, we can obviously use the fourth decimal place only if we needed to. Okay. Oh, there's a little picture. Yeah, I wrote the answer to the question without showing all the work. There's our rejection region. So I'll just do the test statistic and calculator if it's all right with you. Now we're back to stats. So now we're entering in all our numbers. And all right, I don't remember any of this. 160 to 25. And let's see what that was. The mean sample means 183, standard deviation of 12. And it's right-tailed. That's a giant p-value, I mean t-score, and it's really small p-value. So it's safe to say that that 9.58 is way out there in rejection land. So we have sufficient evidence to support the claim that the mean test score for all applicants is greater than 160. Yes, this is not an official term, but in my terms, I call that a monster reject. Even that p-value, that means it's got 9 zeros in front of it. That's automatically, that's going to be smaller than any alpha you'd ever have. So it'd be, you wouldn't have to even write that number out if you're just determining reject or not. You see like an e to the negative 10, you know, or really like e to the negative 4 would be enough, but that's monster reject. So it's, yeah, tiny, tiny p-value. So we reject and we support that claim. All righty. That's it. Except for homework. Go to the homework. Your brain is now full. All right, let's go up here and bring up the new section. 9.3. Now that this class is just about over, at least content-wise, aren't you sad that they don't make the second half of stats requirement anymore? I bet you're sad, aren't you? You'd love another semester of this, wouldn't you? Maybe not. Oh, well. Let's see. That's, well, okay. That's looking up stuff off the chart. Is it okay if I just kind of skip over those? That's, you know, I mean, if you need help, you can always ask me, but that's just taking your n-1 degrees of freedom. And then obviously, well, one tail, I guess you assume for this, I guess assume it's positive because it's not specifying whether it's left or right. I don't like that. I'll do the first one. How about that? Let's see if that's correct logic. Do I even have 0, 2, 5 on my chart? Oh, crap. The book chart's difficult to interpret. Oh, I do. Thank goodness. 0, 2, 5, 28 degrees of freedom. No, wrong column. Glad I went and looked. 20484. Oh crap. 20. It wants 3 decimal places. I already forgot the number. 2084. 2048. 2048. Okay. But I can promise you on an exam, it's going to be clear whether it's intended to be a left-tailed or right-tailed. All right, I'm moving on here. Of course, the two-tailed, you just got to do the plus and minus. I have complete confidence in your ability to do this. Let's get to the word problems. Yes. This is just whether or not you reject. Once again, I don't like the fact this should, well, the critical value being a positive number implies it's a right-tailed test. Yeah, that's bigger. than that, so we would reject. That's just terminology. T sub stat is just test what they use for test statistic. All right. I'm gonna keep moving on here. Looks like just finding the rejection regions and stuff. So this one, I guess you got to do for every part. You're just determining. I'll just do it for part A. So it's kind of hard to see that. It's negative 1.634. So this one, negative 1.75, would be in that blue shading. Another way to look at it is, would positive 1.705 be in the right side shading? And it would. So, but technically, to answer it correctly, it would be D, not B. Even though I just changed it to make it look like B, the right way is to say it as D. But you can use that symmetry logic. Okay. Yes, I want to do that. Every time I do that, it's going to be yes. All right, well, we got a t-test problem here. This could be good. Now we got something going on here. Now we're in business. All right. Okay, what do we got here? Oh, okay, they've already given you the hoe symbol. Well, that's, you just have to know that's the hoe. So the important thing on this problem is you just have to realize that A is never correct because the hoe can't be not equal. So that's really the only part of this. The other two aren't right. Well, that's because they're not right based on what was given up here. Those two, B and D, are logical. They're valid. They're just not the right ones. And then, like I said, A is completely wrong without even reading the question. Test statistic. All righty. Let's bring up our old friend, the calculator here. Calculator is our best friend in this class, isn't it? $52,900. Uh, 51902. Standard deviation, 3,000 and a 16. And I already forgot what tail is this. Oh yeah, it's two tails. Remember that. Two tails. Let's hit enter right here. So we select the two tail. There we go. Two tails. What the heck happened here? Finger slip. Hopefully all the numbers will still be in there. I must have hit that color thing by mistake. All right. Okay. Well, if it only wants two decimal places, I like negative 1.33. Two? Critical values, okay. And a 16. Yeah, notice I always put that parentheses S there, meaning it could be one or it could be plural as in two. This one's two because it's two-tailed. Two-tailed 0.05, 15 degrees of freedom. two-tailed 0.05. Oh, right here, I'm sorry. 15 degrees of freedom. Okay, let's see. This time I looked. It's 3 decimal places. So negative 2.131. Comma, positive 2.131. Look at us go. We are cooking with gas here. All right, now you can look at the test statistic, see whether it fits, or you can go back and look at the calculator and get the p-value and do it that way. Without drawing and save time here, I'm gonna show you the p-value, but this number is definitely between those two numbers. I mean, if you need me to show you, I can, but if you drew the sketches out like I draw, it's between them. So in other words, it's no doubt it's failed to reject. Well, let's look at the p-value. 0.20. 0.20 will be greater than whatever alpha is. 0.05, yeah. 0.20 greater than 0.05. So so like I said, notice these problems aren't asking specifically for the p-value, and I'm wrong. How can I be wrong if those other parts are right here? Is there more choices? Oh, crap. Sorry about that. Yeah, that's. I didn't even read the wording because I thought it was only 2 choices. But now, when there's 4 of them, you got to read the wording. So not enough evidence to reject the claim. Yeah, scrolling down the page would help, wouldn't it? All righty. Okay. Hopefully you can learn from some of my silly mistakes here. Yeah, I just thought it was 2 choices. That's why I didn't even read what it said after it. Wow. This one's another. Let's look and see what we got here. I'm going to come back and probably do this one. Oh, this one's good too. I went the double was a 2-tailed, so I thought maybe this would not be a. Ooh, I want to do that one. So now I'm glad we looked. That's where you got to enter a bunch of numbers in there. I don't know what's going on here. It's probably just a theoretical question. I'm not real excited about it. Here, I'll just highlight the answers where you can say them. So start taking pictures. Number might be different or something, but oh, we could have got B and then that one, no trouble. Well, okay, you're gonna have different. You are gonna have to actually do the calculus. I thought it was just all right. Well, maybe we might take a look. We'll see. Let's see how time goes here. I thought it was gonna be just a bunch of theoretical stuff, but it's an actual calculation problem. Okay. So maybe I will take a look at that one. Well, this one's going to take a little effort here, so let's do this one. Now, I better take a picture of these because it'll take me forever to toggle back and forth into the calculator. I don't know much about how this is done in Excel, so I don't want to waste any time now figuring it out, but if you figure out a way to do it, you can use it. I mean, I can't stop you. But I'm going to do this using the calculator like we did where I had to enter the numbers in. But I need to take a picture of these numbers. So I'm not going back and forth. That way I can read them clearly. Yeah, this will be perfect. I won't have to say anything. I'll do this part first. Oh, this was interesting. It's asking about the claim is which hypothesis. I like that. Let's see, what do we got? Is 98,000. Is will be equal, mu equal 98,000. Of course, that then would pair up, but not equal. All right, I like it. And then the claim is the null. So, fantastic. Critical values, we don't need technology for the critical values. I don't know what they're talking about, but we skip that off the chart. How many values are in it? It tells you 16 in the problem, but we could have counted that if not. So 16 means 15 degrees of freedom, 0.01 is your alpha, two-tailed. 0.01, two-tailed, 15 degrees of freedom. Far right column. .95. Hope it's only one. Well, let me double check. Might want 3. Yeah, I might want 3. I never remember to quit. 2. Oh, not that. So negative 2.95, positive 2.95. Excellent. Look at us go. Ooh, we got a picture. Well, the only picture that, yeah, that's why they're all different. Only one of them is right. But I mean, the only one that represents the two-tailed properly is A. C looks like a confidence interval, but it's definitely A. That's your two-tailed shaded region right there. So, and the other two were left-tailed, right-tailed. All right, now here's where the technology comes in. All right, let me see. Stat, edit, list. All right, so I'm not going to talk here for a couple of minutes. I'm just going to type as quick as I can. I might have to use I wonder if it'll let me use the keypads. If it'll let me use the computer instead of that'll be faster if it will. Oh. Ah. Because I have to use a mouse for the calculator. I'm not touching a real calculator. And I will double check after I enter all of them, see if there's any typos. But I'll just kind of get the base of them all in there. So if you see anything wrong, we'll wait till I get through. Because I'm going to scroll back up and look. No, that's none of those. None of those look. Might have been nice if they picked a problem that used smaller numbers. Four to go. Okay, now let me scroll back up. God dang it. I gotta get rid of that stupid. Okay, maybe got rid of it for me. That accidental slash I put in there. I'll delete it. It's still there. That looks okay. Next four look okay. Those look okay. Five more. Make sure there's nothing there. Let me clear. Okay, I think whatever symbol I had there is. Gotta make sure it doesn't think anything's there. All right, so I'm gonna quit. Stat, test, t-test, data, it's an L1. Let me check that again. I want to say like 98,000. I don't know what it was. 98,000. Okay. Forgot. Okay. It was two-tailed, wasn't it? Yeah. Two-tailed. Well, usually I ask two here, so let's try negative 1.87. Yay. Well, this problem will be extremely rude. You know, I just thought of another way. I'm not going to waste time doing it. I just thought of a potentially better way, more efficient way to do it is if you take those, basically because the numbers are so big, if you took those numbers and dumped them in Excel, and then if you just did the average command on them, and then just did the stdev.s for sample standard deviation, and then just don't use data, use stats, and enter those numbers in there. That might be better. Does that make sense what I said? Yeah, that might be better. See, there's always possible better ways to do stuff. Maybe without redoing the whole problem, I could just do that real quick. Just show you that part. Yeah, that's better than. Well, if it ever opens up here, let's see. So what were our critical values there? negative 2.95, positive 2.95. Yeah, negative 1.87 is clearly between those two numbers. It's going to be do not reject. Do not fail to reject because the test statistic is not in the rejection region. Excellent. The file ever come up? Sometime today. I can't wait for this to open up all day here. Oh, finally. I don't have patience for these things. Oh, I guess I opened it up several times. Who cares? But anyway, you could just, I just picked a cell over there. I could go equals average A1 to A16. And there's your mean. And then I could go equals STD EV dot S. And there's your sample standard deviation. So you enter those numbers in there, and like I said, use the stats instead of the data, and don't type them all in a list. You know, it's too bad I wasn't clever enough to think of that the first time. But I'm glad I thought of it at least now, so that might be the way to go. All right. All right, so we got more to this here. There is, so the claim, that's the key here. The claim was the hoe. Well, it's level of significance. We can put that in there. That's 0.01 is 1%. But I got to read all this before I get this. So we did not reject. So I'm going to say there's not enough evidence to reject all right, let's see how this did. That reject might need to say support. Let me see. No, okay. I'll try to outthink myself there. That was it. All right, let's plow through here, man. We'll try one more, and I think that'll. Let me go back. Maybe I could do this one that I skipped over earlier. So I was going to do this one of these, this one, or something else. I did that one, so I don't know. You want to shout something at me, or or whatever? Do you have a preference, or? I mean, any of these are fine. Let's see. Let me just look and see what all the parts are to these, and just to see. Well, this was a little different. I don't know if this one goes quick enough. Maybe I'll do this one and that last one. All righty, let's see what we got here. Is 20,000. There's our key. Equal, not equal. Remember, equal's got to be in the right spot, doesn't it? Equal has to be the hoe. And boom. Critical values, two of them. Alpha's 0.01, two-tailed, 22 vehicles, 21 degrees of freedom. 0.01, two-tailed, 21 degrees of freedom. Last column. $2.8314. So 2.8314 would just be 2.831, negative and positive. Tremendous. So, this is interesting because this is actually not correct, but I'm glad we did this one now or whatever. I wish there was somebody could go manually edit that. It's C, but C, it should not be the word and, it should be the word or. That's not logically right, but it's the right answer for this question. So yeah, I'm not going to get rid of the whole problem because of that, but so you guys and anybody watches this later, then we'll see that I just explained it. So, but that's really not right. The shape of it's right. You just change the word or in there. Yeah, I wish I could directly fix that. So it's t less than the negative or t greater than the positive. So it's right, but it's not right. Test statistic, all right. Sounds like our friend the calculator is going to go to work here. Stats. $20,000. Sample mean 2738. Oh, I see it. Let me put this first. I'm shy of 0 up here. Standard deviation, 1949. 22, I believe. And this was a two-tailed test. Test statistic. If it's 2 decimal places, well, I'll just say 1.776. So I'll remember that third one in case I need it. 1.78, I don't need it. All right, I can look at the p-value. I can look at this also. All right, that 1.78 is going to be between those numbers. It's going to be in the middle. It's not going to fall in either rejection zone. So we learned from a mistake earlier. Yeah, so make sure you realize there's 4 of these, but we fail to reject because the test statistic is not in the rejection region. That makes sense logically. B doesn't make any sense because fail to reject because it's in the rejection region. Huh? You know, if it's in the rejection region, that would mean reject. Fantastic. All right, so first part's all the same. So the claim was the hoe equals, and we failed to reject. So I like A. There's not sufficient evidence to reject the claim. The mean price is 20,000. Doesn't mean we love it, but we did not have the evidence to reject it. Well, it's either this one or that last one, or or neither. I can stop, whatever you want. You're probably pleading for me to stop. You can yell into the screen if you want to, but let me see. We might get this one pretty quick, though. Yeah, we'll do this one. All right, assume the population is normally distributed. We're definitely going to be using a T. And actually F would be the right answer there. A lot of times the ends will be less than 30, but that's not the primary reason. This is the primary reason because the population is normal and we don't have the sigma, the population standard deviation. So that's the key. Hypothesis test, at least means greater than or equal to. That'll be the ho. The ha will be less than. Nice work. Test statistic, there we go. All right, 20. Sample mean, 17. Standard deviation is 4 and sample of 7 cars. So N is 7. So that'll be 4, N is 7. This is a left tail test because at least greater than equal to pairs up with less than. All right, let's see if negative 1.98 is what we're looking for. Critical value will be one value because this is not a two-tail test, and it'll be a negative. Left-tailed, so N is 7, so it'll be 6 degrees of freedom. Alpha is 0.05. So I need one tail, 0.05, 6 degrees of freedom, but that'll be negative. I like that one. So I'm going to go negative 1.943. Negative 1.9, okay. Negative 1.943. Excellent. Ooh, these numbers are close, aren't they? You might well, like I said, we can use the p-value if you want to instead. But if you try to think through it this way, so the critical value is negative 1.943. Double check that. Okay. Yeah, this is tricky. Negative 1.98 is just barely inside the rejection zone. But like I said, suppose you want to move this over, and I don't know about this, and then I'm going to look at it this way. But be careful how you answer any wording in the question. But now might be easier to understand that 1.98 positive is greater than 1.943. The negatives are a little tricky. Now, the p-value is obviously going to be very close to alpha. So if this is a very close reject, it's got to be close on all levels. But let's look and see. So the p-value is what's 0.05. Yeah, look, alpha is 0.05. So p is 0.047, which is barely less than 0.05. It's less, barely less, but that means reject. So we're going to definitely reject the hoe. And the claim was the hoe. So we rejected it. Let me see. Yeah. So there is sufficient evidence to reject cars claims at least 20 miles per gallon. Well done. Okay, that'll conclude the content portion here. I'll go ahead and just make this easier for myself and put this on pause recording. And obviously, I'm going anywhere, but that way I don't have to edit that stuff out later, whatever happens after this. Nothing bad's going to happen, but I mean, I could even stop it, I guess. But no, I'll